Today we're going to talk about dynamics. So first, state of motion. There are two big different categories of state of motion. First, when an object is at rest or moving at a constant velocity, we say those two are two big state of motion. However, if an object is changing speed or direction, it is not a state of motion. So the big topic in this chapter, dynamics, are forces. We're going to be talking about various kinds of forces, how these forces interact, how to calculate the net force, which is the vector sum of the force acting on an object, and how these forces change acceleration. For example, if this object if there's 10 newtons pushing towards the left direction and 5 newtons of power pushing towards the right direction, the F net, which is the vector sum of forces, what would the F net be? It would be 5, because 10 to the left and 5 to the right, 5 from each would cancel out, and 5 to the right would be left. So F net would be 5. And then for the next example, it's not as simple, right? We have diagonal forces as a result of 3 pushing towards the right and 4 pushing towards the up. If we draw a triangle, 3 towards the right and 4 up, we can realize that this is a common triangle. So that would be 5. So F net is also 5, because we know that 3, 4, 5 is a common triangle, we know. However, compared to these two cases, if there's 5, 5 on each acting towards each other, F net would be 0, because they cancel out. And similarly here, if we see 3 towards the right, 4 up, but 5 back down, the 5 here cancels out these two. So the F net here would also be 0. So here, these two cases are called unbalanced forces. These cases are called balanced forces. When F net equals 0 and all the forces cancel out, they are called balanced forces. So moving on, inertia the definition of inertia is object's tendency to continue motion. So motion is going to be a big concept that we're going to be talking about today, because it connects to the Newton's law of motion. So first, as we've been talking about the law of inertia, if F net, which is the sum of all forces that is acting on an object, if F net equals 0, the velocity cannot change. So if F net equals 0, it means we have a constant velocity and acceleration equals 0. But why? Because if an object is let's say that a ball is already rolling on an ice field where we're gonna assume no friction. If a ball is already rolling and there's no other forces that's acting on, in an ideal world where there is no friction, the ball is going to keep moving in that same direction and that same speed if there's no other force acting on, right? So F net equals 0, meaning that there's no other external forces acting on. The velocity cannot change because there can be no acceleration on the object. Now moving on, the law of acceleration. This basically, here we find the famous equation that we've been hearing, which is F net equals ma. It is important that we write F net, because if we write F equals ma, this equation is wrong. So we can see that, through this equation, we can see that the F net equals mass times acceleration of the certain object. So let's apply this equation. For example, if we see an object that that's mass is 2 here, and is being pushed 5 towards the left and 7 towards the right, we'll apply the equation right here where F net equals ma. So what's the F net? The F net is 2 because it's pushing 5 towards the right and 7 towards the left. So 5 will cancel out and 2 will be left towards the right. So F net equals 2 and mass here is 2, right? So the acceleration would naturally be 1. So here we'll find out a relationship between mass and acceleration. So let's say that under the same circumstance, let's say that the mass is 1, not 2. Here, acceleration would be 2, right? So we can see that if the same amount of force is being acted upon an object, if the heavier the mass, the slower the acceleration. And the lighter the mass, the higher the acceleration is the relationship we can find. Lastly, the law of opposite forces and action and reaction. So the law of opposite forces and action and reaction shows that there is always an equal and opposite force. This means that this equal and opposite force is same or equal in magnitude, but B, opposite in direction. So here, for example, if a person called Albert is pushing the wall with 10 newtons, the wall, although it is counterintuitive, the wall is pushing Albert back with 10 newtons. And that is why Albert nor the wall is moving. If this 10 newtons of the wall pushing back did not exist, Albert and the wall would be moving towards the left direction because it is an unbalanced force. So it is true that the wall needs to push back with 10 newtons, opposite in direction, but same and equal in magnitude. So whenever you're identifying the opposite force, we can call it the opposite force or the reaction force. So whenever we're identifying the reaction force, I always find it easy if we use simple and clear words. So Albert push wall, and wall push Albert. So here, another example where Bob and Steve is pushing each other. Let's say they're on an ice rink and Bob and Steve pushes each other and goes apart from each other. So here we're going to use the equation F net equals ma, and Bob for Bob, F net is 5, right? 5 towards the left because they're being pushed off, and Bob is pushing 5 newtons and Steve is pushing 10 newtons. So 5 equals, because Bob's mass is 5 times A, and Steve 5 equals 10 times A. So here A would be 1 for Bob and A would be 0.5 for Steve. So there are various types of forces. Although we've talked about the action and reaction force, the applied force and all that, there's 4 big types of forces that we're going to talk about in AP Physics 1. So this is an acronym used to memorize these 4 types of forces. You can memorize it as what the force Newton. So weight or gravity and tension, friction, and normal force. So these are the 4 big types of forces that we're going to study in today's chapter. Okay, so today in this chapter, we're going to study a bunch of different examples because I feel like drawing like free body diagrams and exploring these various types of examples will help us understand the concepts of different types of forces and help us learn to calculate the acceleration or the amount of force in different types of situations. So first, let's say that there's a box that weighs a mass of m, and there's a rope attached to it. So here, if we draw a free body diagram, a free body diagram is where we draw the forces that are acting on an object. So here, there will be the force of gravity, which is mg, and the normal force, because here, according to the Newton's law, we know that there is always an equal and opposite force that is acting on. So that would be the normal force, and these two would be equal to each other, and therefore cancel out. And this is why the box is not moving up or down, because there's an equal force up and down. And then there's a tension force. So F net equals ma, right? So the F net, the net force that is acting on this box, is tension. So here, tension would equal mass times acceleration. Moving on to the next example. Here, let's say box of M1 and M2 is stuck together with each other, and there is a force, the applied force of 20 newtons pushed towards the right direction on the side of M1. Let's assume that M1 is 3 kilograms and M2 is 2 kilograms. So here, there would be Fg and the normal force for both boxes. But we know that they cancel out because the boxes are not moving up and down. So when we're solving problems, we can disregard them. But we do know that there is a force, a normal force, being acted upon between the two boxes. So we'll call, if we zoom in, we can say that's also n. We will write two different equations for two different boxes because it's easier to understand. So for the first box, the M1, this box, we'll say that 3a equals 20 minus n. So this is the case because F net equals ma again. So this would be the F net, and that would be the ma, because we're assuming that m1 is 3, and then times acceleration equals. Why is it 20 minus n? Because, not n minus 20, because we're assuming that these two boxes are moving towards the the right direction. So it would be 20 newtons to the right minus this n that's acting the opposite direction of 20 newtons, so it would be 3a equals 20 minus n. The second equation for this box would be 2a equals n, because n towards the right direction is pretty much the only force that is being acted upon the second box. So if we add these two equations, we get 5a equals 20. So therefore, a equals 4. The unit for acceleration is always meter per second squared, so from this we can find out that the acceleration is 4 meters per second squared. Moving on to the next example. Here, again, we see two different boxes attached with a rope. So we know that there is a force, gravitational force, normal force for both boxes, but we can disregard them in terms of calculation. But we do know that there is a tension force applied for both of the boxes. This is something to note, that a tension force throughout the whole string or a rope is always constant. So these two tension forces should be equal. So first, we'll separate this into two different diagrams. So that can be 1 and that can be 2. So first, let's write the equation for M1. So again, we're assuming that M1 is 3 kilograms. So 3a equals F net, which is T, because these two cancel out, and T is pretty much the only net force that is acting upon the box. And for the second box, 2a, because we're assuming that M2 is 2 kilograms, equals 20 minus T, because again, we're assuming that these boxes are moving towards the right direction, and therefore, it's 20 newtons this is a larger force than T. So 20 minus T, since T is acting towards the opposite direction as the 20 newtons. So if we add these equations, we get 5a equals 20, and therefore a is 4 meters per second squared. So for this problem, we see a pulley. And we're supposing that the pulley has no mass, because if the pulley has mass, the problem becomes complicated, and we need to know other advanced concepts. So in AP Physics 1, we're going to assume that the pulley has no mass. So for the first box, we have, again, the gravitational force and the normal force. And we also have a tension force, again, towards the right direction. And for M2, we have a gravitational force and, again, a tension force acting up. And therefore, here we're assuming that M1 is 3 kilograms. So let's, again, start with this box. So 3a would equal T, because again Fn and Fg will cancel out because they're the same and opposite forces, and Ft would be the net force that is acting on M1. And then for this diagram here, we would have 2a would equal, now Fg equals ma, right? So, but here the only acceleration is gravity. We need to note that gravity is, when we're calculating gravity in AP Physics 1, we can calculate it as 10 because it's precisely 9.8 something something something, but we round it up to 10. So this can be rounded up to 20. So 2a would be 20 minus t. So if we add these two up, we would get 5a equals 20, and therefore a would equal 4. Again, why is it 20 minus t, not t minus 20? Because we're assuming that M2 is moving downwards. So here, the 20 newtons downward is a larger force than Ft. So we're subtracting t from the larger force, which is 20. Next, what happens to a person's scale in a moving elevator? So scale is a little bit of an advanced application concept. Scale in a moving elevator. When you normally step up to a scale, the scale measures your weight, right? But it doesn't measure your gravitational force. The number in the scale is actually the normal force. So here, the scale shows the normal force of the person standing on the scale. So note that is what the scale is showing. So in the moving elevator, what would happen to the number shown in the scale? Intuitively, we would think that because the person standing on the scale's mass is constant, the person's not going to become like heavier or lighter while the elevator is moving. So intuitively we would think that the mass, because since the mass is constant, the numbers shown in the scale would also be constant. However, again, because the scale is not measuring the mass but the normal force, the number in the scale is changing. When the normal force is equal to mg is when the elevator is at rest or moving at a constant speed. However, when is the net force larger than the mg? So when would the scale show a greater number? When would the scale tell you that you're heavier than you actually are? When the elevator is accelerating up and when it decelerates down. So what it means by decelerating down, it's basically slowing down, but it's still going down. But how is that accelerating equal to accelerating up? Because slowing down towards the downward means that it's accelerating upward. They both apply to when Fnet is larger than mg. When Fnet is smaller than mg. So when would the scale tell you that you're lighter than you actually are? When it's decelerating upward or accelerating downward. So the next example is an inclined surface. So here, that would be the mg, and that would be the Fn, because we always know that the normal force is perpendicular to the surface. So to solve this problem, we're gonna decompose this vector mg. So that vector mg is equal to that vector and that vector. And here, we know that that theta right there is equal to this theta, and that theta is also equal to that theta. If we know that this is mg, and we know that in this triangle and this triangle, this theta is equal to this theta and this theta, due to trigonometric knowledge, we know that that vector right there is equal to mg sine theta, and that vector down here is equal to mg cos theta. So because the normal force and the mg cos theta force is acting opposite to each other, but the block is not moving upwards nor downwards, these two should cancel out and equal each other, and therefore the F net is mg sine theta. And the mass cancels out from each side, and the acceleration would equal g sine theta. Now moving on to the last big concept of today's chapter, friction. So we're going to assume that there is a block right here, and there is a force pulling the block towards the right direction, but there is a friction force applied between the block and the floor to the opposite direction, the force of friction. So this is a chart that I made, and let's say that these are the values for the force, and these are the values of the friction recorded at different time periods. So here, up to this is when the block is still at rest, but the force is increasing, but the block is still at rest. And this is when the the block starts to slide. So when the block is still at rest, but the force is still increasing, all of these friction forces are called static friction. And that is called the maximum static friction, because it's the maximum static friction right before the block starts to slide. So as soon as it hits 60.01, this is the maximum static friction value is different for all the cases, because there is a different threshold for every different examples in the world. So in this case, as soon as the force becomes higher than 60, the block begins to slide. So all of the friction applied when the block is moving is called kinetic friction. So from this chart, we can find out that there's basically two different types of frictions: kinetic friction and static friction. So these are the equations for finding the kinetic friction and static friction. And we notice that it is mu k times Fn is equals to kinetic friction, and mu s times Fn equals to static friction. So what is mu? Mu is the coefficient. So to understand the coefficient, we need to understand the concept of roughness and how it relates with friction. So let me ask you a question. Is it harder to pull up box in an asphalt where it's very rough and bumpy, or is it easier to pull a box on an ice rink where the friction is basically low? The answer would be it's easier to pull it in an ice rink than an asphalt and this is because the coefficient of friction is lower in ice than it is in various different surfaces. So all the different surfaces have different coefficient of friction. So applying the knowledge we just learned, this is an example we did previously, but how will it change based on when friction is applied? So same concept, there would still be mg and Fn. And we will still decompose this mg into two different vectors. And that would be mg sine theta and mg cos theta. However, now we have another force called F friction. So because because this and this needs to cancel out, we know that Fn equals mg cos theta. And so we know that these two forces cancel out. So basically, if the box is at rest, we know that mg sine theta needs to equal the force, needs to be smaller than the force of friction, which is mu s Fn. However, at the moment of sliding, at the exact moment of when the block begins to slide, mg sine theta equals the amount of friction, which is mu s Fn. But we know that Fn here is mg cos theta. So this would be mg cos theta. And we can delete the m's from each side, and therefore we know that mu s equals sine theta over cos theta, which is equal to tangent theta. So today we learned about the general chapter of dynamics and different types of forces. And we talked about various different situations and how in these different situations there are different types of forces that are being applied, and how the different types of forces change the net force, and how this impacts the acceleration of an object in various cases. So next chapter we're going to talk about work and energy, and this is going to be a slightly different concept, and it's going to connect to different types of forces. So thank you and stay tuned.